Okay, the rules of resonance. Before we get into the rules of resonance, we need to go over curly arrows. Curly arrows. Now, we will deal with them a lot more, but they look like this. It is literally a curved arrow, and the convention is that the arrow originates where the electrons are and points to where they are going in the next sequence. So, as an example, if I wanted to show a resonance structure of our old friend now, I would show the arrow coming from the negative charge and going to where the bond is going to be formed, i.e. the new pi bond. And we would show one pi bond breaking, the electrons coming from the bond going to the oxygen. So in our next structure, we would now show where the electrons went. So we now happen to have a new double bond because the electrons moved to form that pi bond, and a negative charge on the oxygen because that's where the electrons ended up according to this arrow. Let's put some color on it because I'm starting to learn how to use this stuff. So this bond came from that color, and this bond with the arrow ends up being up here. Alright, cool. Hope you guys are watching, not just listening, because I'm not explaining myself that well. Alright. So we have rules of resonance. Well, rule 1, atoms cannot move. Only electrons in pi bonds or conjugated p-orbitals may move. So as we discussed in the previous video, if you understand conjugation, you can figure out which electrons should be able to move and which ones do not. Now, practice makes perfect, just practice it. Alright, each resonance structure, rule number 2, each resonance structure must have the same number of electrons and the same charge. Now, of course, something can have multiple charges. Say, for example, this conjugated system. If these electrons move along, we are not going to end up with the same charges. But we think about what's happening. New bond formed here. This carbon lost electrons, so it must have a positive charge now. This double bond broke, and we now must have a negative charge over here. So let's put some color on it so we get an idea. This double bond here, only a double bond here, and this double bond here formed a negative charge. Now, of course, the positive charge wasn't anywhere. It formed because the electrons moved away from that carbon. But overall, charges cancel out. Therefore, both are neutral. Yes? We agree? Good. Moving on. Rule number 3 discusses stability. So the stability of a resonance structure determined just like any other Lewis structure, determined by the octet rule. It is determined by the charges and the interactions of such charges. So we'll go back to our previous example. Both of these can be a thing. They are resonance structures of each other, but this one is most stable of these two resonance structures because it doesn't have any charge. Why else? Well, does not comply with the octet rule. Could be a thing. What if we did this resonance structure where both of these moved away so that we have a negative charge, a positive charge, and a positive charge and a negative charge? Oof. Well, of course, this is a terrible resonance structure. It's not going to help at all because we're not avoiding charges. But you can also tell that, well, if we have two atoms next to each other and they happen to have the same charge, they are going to repel, and therefore you're going to get a decrease in stability. So keep those things in mind when you are drawing resonance structures. Rule number 4, the actual structure of the compound must resemble the most stable resonance structure. So if you're trying to figure out what the reactivity of your compound is, the best way to figure that out is to first draw the actual resonance structure you are discussing, because the most stable resonance structure will be how the compound is most likely to react. Of course, if you know certain things, you'll then be able to go by functional groups and discuss those, but until we get to that point, don't worry about it. Also, finally, as the number of resonance structures increases, the stability increases. Alright, what does that mean? Well, let's go with this compound here versus this compound here. Which one of these two is more stable? Well, we'll go with the first one. There's not much else going on for it except that it can resonate, so we'll resonate. It can form this resonance structure, and it can keep on moving with its arrows to give you this resonance structure. Okay, so number 1 with number 1. Go with 2. This is 2, sorry. If we start drawing resonance structures, we have 1, 2, and 3 resonance structure. So overall we have 1, 2, 3, 4 resonance structures versus 1, 2, and 3 resonance structures. This would directly tell us that number 2 is more stable because more structures.